As a poster child for the application of generating functions, next we're going to take a look at the Catalan numbers, which are a fundamental sequence of great interest in combinatorics. One way to, there's many applications of the Catalan numbers, and I'll give a few. So one of the earliest that people thought about was how many different ways are there to take a polygon with n plus 2 sides and draw lines from one vertex to another and make it all triangles. So for example, if you have a pentagon, you have all these different ways to triangulate it. Well, actually, it's easy. You just draw from any vertex, you draw to the two opposite, and the 5 vertices, you get 5 triangulations. Or if it's a square, you just get 2. But if it's a hexagon, there's lots of possibilities. You can do 3 like that, or you can do these N shapes. There's lots of possibilities. And actually, it turns out that the number of triangulations of a hexagon is 14. So that's a number sequence that is described by this recurrence relation over here. In general, if we draw and leave k, we draw a diagonal and leave k vertices on one side and n minus 1 minus k on the other side, and there's one less because we draw the triangle, then you can triangulate those any way that you want. And each one of them independently. So it says that the number of triangulations has to satisfy that recurrence relation. Sum from 0 to k less than n, tk, tn minus 1k, plus an extra, because there's always one way to triangulate the triangle. So that's a recurrence relation that we're going to take a look at solving. But it applies in many other applications. Here's another application, the so-called gambler's ruins problem. So you're a gambler and you start with $0 and you make $1 bets. And if you win, the line goes up. It's just a graph of amount of money that you have. So in this case, there's 2 wins followed by a loss, win, loss, 2 wins, and then a bunch of losses. And the idea is the gambler will keep going until having $0 makes a bet and loses, and then the game's over. And how many different ways are there for the gambler to do that with, say, n wins in the sequence? Well, there'll be n losses too. And again, if you try out all the possibilities, it turns out that there's only 2 possibilities. If there's $2, you can win, lose, lose, or you can win 2 and then lose 3. And those are the only 2 possibilities. And there's 5 different ways for 3 wins and 14 for 4 wins. And same sequence because it satisfies the same recurrence. You can just set up the recurrence by the first time the gambler gets back to 0. If that happens after k wins, then independently you have a gambler's ruin problems on k and on n minus 1k, and it follows the same recurrence. Here's another one, binary tree structures. So a binary tree is a root node that is connected to 2 binary trees, a tree on the left and a tree on the right. Or it could be empty. That's called an external node. So how many different binary trees are there with n nodes? And we'll look in a lot of detail at binary trees later on. So there's 2 different binary trees with 2 nodes. So that is, you got one at the root, and you could have a 1-node tree on the left or a 1-node tree on the right. And every node has to have 2 children, and the ones at the bottom have 2 blank children. Those are called external nodes. For 3, there's 5 possibilities. You have a node at the root, and it could be empty on the right with either one of these trees on the left, or it could be empty on the left with either one of these trees on the right, or you could have 2 trees of size 1, one on either side. So there's 5 possibilities for 3 nodes. And similarly, there's 14 possibilities for 4 nodes. So you could have empty on the left in any one of the 3-node trees, empty on the right, any one of the 3-node trees on the left, empty on the left, any one of the 3 node trees on the right, or you can have 1 on one side and 2 on the other side in 4 possible ways. So again, same number sequence, again, satisfies the same recurrence. If you've got k nodes on the left, you're going to have n minus 1 minus k nodes on the right, and you can try all possibilities on either side, so it's got to satisfy the recurrence where t is n is equal to the sum for all k up to n minus 1 of tk, tn minus 1 minus k, plus a delta term to make it true for 0. Catalan numbers. Here's another one. How many trees with n nodes? A tree is a node connected to a forest of trees, to any number of trees, so it's not restricted to be just 2. And again, we'll talk in detail later in the course about trees and binary trees. But for now, I just want to point out all the possibilities and satisfies the same recurrence. So Catalan numbers describe a lot of combinatorial objects of interest. So how are we going to solve the Catalan recurrence with generating functions? Well, we're going to use the formula. We got the recurrence that holds for all n. Now we're going to, what's the next step? It's multiply by z to the n and sum on n. On the left-hand side, that gives us t of z. That's the generating function for the Catalan numbers. On the right-hand side, we'll get a 1 for the delta term on the right, and then we get some n big equal to 0, 0 less than equal to k less than n, tk, tn minus 1. That looks familiar. It is familiar. We're going to work backwards from the convolution derivation that we did before. So now what we'll do is, first thing we'll do is switch order summation. So switching order summation means if you're going to try for every value of k, then the inner sum is just for n bigger than k. Now in that inner sum, we'll change n to n plus k plus 1. Change n to n plus k plus 1, n bigger than k, that's n bigger or equal to k plus 1, so that's the same as n bigger or equal to 0. And then the t sub n minus 1 minus k just becomes t sub n, and then we have z to the n plus k plus 1. And that gives us a way to split it into independent sums by distributing the k's and the n's. And then you can see immediately the 1z comes out, and then it's 2 copies of the generating function t of z. So that's a backwards convolution that shows us that the Catalan generating function has to satisfy this functional equation. T of z equals 1 plus z times t of z squared. So we're halfway there. We've got an equation that the generating function has to satisfy. Now, a common sense rule for working with generating functions that I want to point out, again, it's always worthwhile to check your math with your computer, and that includes symbolic calculations like this one. You know the initial values of t of z. We did the examples, so we know that it starts out being 1 plus z plus 2z squared plus 5z cubed plus 14z fourth. Before we go any further, we might want to check that this equation that we have really holds. And you can do it in pencil and paper, or you can use a symbolic math system, and you can see that if you take 1 plus z times 1 plus z squared and so forth, I just took it out to 4 terms here, the ones that we know. If you multiply them out, you get 1 plus z plus 2z squared plus 5z cubed plus 4z fourth, and so forth. Now after a while the terms are no good because we didn't take these terms far enough, but still that gives confidence, and actually you can bootstrap this to get more terms, but it gives confidence that we've got the right equation. So that's just checking your math with the computer even when it's symbolic. All right, so now what we need to do is to extract coefficients to find an expression for the nth Catalan number. So that's the GF equation. Well, it's an equation that we know how to solve with the quadratic formula. And so that's the solution with the quadratic formula. just applying the 8th grade formula. And then we have to pick 1 plus or 1 minus, and it's going to be the minus. So just I left out that one consideration, and that you get from checking with the initial values. So now, how do we deal with that? We expand 1 over square root of 1 minus 4z. We just use the binomial theorem. It's 1 minus 4z to the 1/2 power. So it's the sum of 1/2 choose n, 4z to the n. And then this one part goes away. And so, and again, we can check that from initial values. So that's a key step for this generating function. We have a solution that uses the quadratic formula, and then we have an expansion of a function that we know how to expand, know how to find coefficients. So that tells us what t sub n is. It's minus 1/2, 1/2 choose n plus 1 minus 4 to the n plus 1. This extra z is what leads to the n plus 1s. Now that's it's okay. It's not totally satisfying because the 1/2 n plus 1 is maybe not such a familiar function. And there's a way to manipulate this to get it to be a little bit more familiar function. And actually next time we'll talk about a much better way to continue to manipulate it to get really a concise representation. But let's just do just a little more algebra to get this in more of a form that we can people can relate to. This is the definition of the binomial coefficient when the upper index, for any binomial coefficient, it's on the bottom is n plus 1 factorial, and on the top is n plus 1 terms where we subtract 0, 1, 2, all the way up to n. So that's just the definition. And there's the minus 1/2, and there's the minus 4 to the n plus 1. And so now what we're going to do is take, we have n plus 1 terms here, and we've got n plus 1 fours, and we're going to take a bunch of those. We'll take the n plus 1 minus 2s and multiply them in. And one of them kills that, and then the others you get 1, 3, 5, all the way up to 2n minus 1, like that. So that's a slight trick, but cleans it up quite a bit. And now, if you have that, then if you fill in the evens, so 2 to the n is 2 over 1 times 4 over 2, and so forth. So now we have the odds and the evens, and we have an n factorial. So that's going to immediately give us 2n factorial over n factorial times n factorial, which is 2n choose n. So that's a proof that the number of binary trees on n nodes, number of general trees on n nodes, the number of ways to triangulate n plus 2 con, and so forth, the Catalan numbers is 1 over n plus 1 times 2n choose n. And that's one of the most famous number sequences in combinatorics. And we'll see in many cases we explicitly use data structures like trees in practical algorithms and data structures, so we need to understand these properties of them. And we're going to continue working with the Catalan numbers on several other occasions later on in the course.